All right, the next example is a table problem, and we're given selected values of f and g and their first derivatives in the table. We are told that h is the function defined by, and there you go, h of x is f of x times g of x minus x squared. All right, our first task, evaluate h prime of 3 and h prime of 0. Before we can evaluate a derivative at a particular value, we must have the derivative in terms of x. So we must find h prime of x first. And if you're looking carefully, h is f times g minus x squared. So we must apply the product rule to the first part of that derivative. So finding h prime of x, I'm not going to plug in a 3 or a 0. I'm going to use the product rule, derivative of the first, so f prime times the second, g, plus derivative of the second, so g prime times the first function, f, and that is the product rule. So that piece of our derivative is what I highlighted in yellow above. However, we still have this minus x squared, and so we take that derivative too, and we have minus 2x. All right, so this whole thing is the derivative of h with respect to x. Once we have found that derivative, we could now evaluate h prime of 3, and I'm going to just literally replace every single x with the number 3. Just a heads up, for a free response question, you would be expected to show h prime of x, and you'd be expected probably to show your work here for h prime of 3. All right, so we get f prime of 3, which is 0. I'm going to say equals 0 times, well, I already know I'm multiplying by 0, so it's kind of moot, but just for the sake of the example, g of 3, which is 1, plus g prime of 3, so in my table, g prime of 3 is 4, times f of 3, which is negative 3, and then minus 2 times 3, so minus 6. So 0 plus negative 12 minus 6 is negative 18. So h prime of 3 is negative 18. And then we just repeat that process to evaluate h prime of 0. I didn't leave myself a lot of room. H prime of 0, well, that's going to be f prime of 0 plus, or sorry, not plus, times g of 0 plus g prime of 0 times f of 0 minus 2 times 0. All right, f prime of 0 is negative, nope, that's g. It would help if I could read. All right, f prime of 0 is 7. G of 0 is negative 2. We're going to add to that g prime of 0, which is negative 2, times f of 0, which is 1. And we know 2 times 0 is 0. So negative 14 plus negative 2 is negative 16. So h prime of 0 is negative 16. All right, part B, find the equation of the line tangent to h at x equals 3. So if you think about our point slope form, y minus y1 equals m times x minus x1, our point of tangency is x1 comma y1. And we already know that that x value of our point of tangency is positive 3. So if we find h of 3, let's see if we plug that in, h of 3, I'm going back to my original function, not my derivative. So that's going to be f of 3 times g of 3 minus 3 squared. All right, so let's see. F of 3 is negative 3. G of 3 is 1. 3 squared is 9. Negative 3 times 1 minus 9 is negative 12. So the ordered pair 3 comma negative 12 represents the point at which our tangent line intersects our function h. That is our point of tangency. So the other thing we need is the slope. And remember, the slope of our tangent line, aka the instantaneous rate of change of h at x equals 3, is our derivative. So h prime of 3 is the slope of our tangent line. So in my table, oh, not in my table, in part A, where I already found h prime of 3, we said that is negative 18. We don't need to do that again if we already know that. So just putting that all together, y minus negative 12 becomes y plus 12. That equals our slope m, negative 18, times x minus 3. And that is the equation of the tangent line. There's no reason to rewrite that in slope-intercept form. You could, but don't. It's just an opportunity to make a mistake. All right, lastly, part C. Use the equation from part B to approximate h of 3.1. So I'm just going to pop this down from part B. And if I'm approximating h of 3.1, that's going to be approximately equal to what y is equal to when we substitute that for x. So y plus 12 equals negative 18 times, I'm going to substitute 3.1 for x minus 3, bam. All right, order of operations, 3.1 minus 3 is 1/10. So y plus 12 is negative 18 times, sorry, it's a funny looking 8, times 1/10 or 0.1. And then if I multiply, you all know how algebra works, we get negative 1.8. And then I could subtract 12 from both sides. So y equals negative 1.8 minus 12, negative 13.8. Okay, so when we get that value for y, just a point of, like, it's a small meticulous point. That is an exact value for y because we use the equation that relates x and y to get that value. That is an approximate value for h of 3.1. And if your next question is, will I be docked if I don't use the approximately equal symbol on the AP exam, I would say it's unlikely. If you write h of 3.1 equals negative 13.8, I don't think they will count you off. It's just not exactly equal. All right, this very last section, we're going to do just a couple examples. I might skip a few of these. On page 29, our goal is to memorize our trig derivatives, but we can always derive them, aside from sine and cosine, using the quotient rule. Let's look at one example with the quotient rule, and then we'll skip ahead. Okay, so find dy dx if y equals the tangent of x. In other words, take the derivative. Okay, so we don't yet know, unless you've looked at the rest of the spiral or the next page, we don't know the derivative of the tangent of x yet, but I do know from geometry and from trig that the tangent of x is the sine of x divided by the cosine of x. So now that we know a quotient rule, we can take the derivative of the sine of x divided by the cosine of x. All right, so using that little, using the quotient rule, I'm going to say the little saying because I have to. We could do low d high, so that's the cosine of x, times, well, d high, the derivative of sine, is also the cosine of x, minus high d low, so the sine of x. Remember, the derivative of cosine is negative, so we're going to multiply that by the negative sine of x. All of that over low, the cosine of x squared. Remember that with logarithms and with trigonometric functions, we write the square between COS and between the argument so as to not be confused with the cosine of the value x squared. All right, so if I were to reorganize this, cosine of x times cosine of x is, again, the cosine squared of x. Sine times negative sine is negative sine squared. So instead of minus negative sine squared, I could write plus sine squared of x. And then all of that over the cosine squared of x. Now, this is not our final answer, or at least this is not how we want to write the derivative of the tangent of x. And we might need to remember one of our Pythagorean identities from trig, that cosine squared plus sine squared is 1. And if you just think about the unit circle, we know on the unit circle the hypotenuse is 1. If I think about There's the sine of x, there's the cosine of x. This is just the Pythagorean theorem. So a squared plus b squared equals c squared. Sine of x squared plus cosine of x squared equals 1 squared, which is just 1. So for our final y prime, well, almost our final, we could rewrite the numerator as 1 over cosine squared of x. But let's also bring back that reciprocal identity, because 1 over the cosine of x squared is just the secant squared of x. So we do need to remember a few of those identities from trig, but don't you worry, we'll have lots of time to revisit those. So at the end of the day, the derivative of tangent of x is the secant of x squared. We could derive all of our trigonometric derivatives that way once we know sine and cosine, but let's just instead memorize them. So what I would point out to you is that all of the cofunctions, so cosine, cotangent, and cosecant, they all have negative derivatives, or I should say at least of the opposite sign. Otherwise though, if you notice, the derivative of a function and the derivative of its cofunction are similar, but we switch to the cofunction. So here's what I mean. The derivative of sine of x is cosine of x, whereas the derivative of cosine is negative sine. The derivative of the tangent of x is the secant squared of x, which we just proved. The cofunction, cotangent, it is negative cosecant squared. And then lastly, the derivative of the secant of x is secant tangent, whereas the derivative of the cosecant is negative cosecant, negative cotangent. So if you can just memorize the first three, the sine, tangent, and secant, then you know that when you take the derivative of the cofunction, it is negative and it's the cofunction, or cofunctions in the case of secant. All right, let's just look at 1 to 2 more examples. I know you're getting sick of doing this because I'm getting sick of making this video. That's how I know. I think these will go quickly. All right, let's look at this second example on page 30. I'm going to skip the first one. Oops, that was supposed to be a highlighter. If we are finding the second derivative, y'all, I'm super lazy and I will say f double prime of -1 and I'm fine with that. I know exactly what you mean if you say that, but that is the second derivative of f with respect to x. So we always have to find the first derivative. I can't just jump to the second. So we have to be careful that we make sure we use the product rule here. And the bummer is that the product rule always generates multiple terms. So when I take the derivative of x to the 5th times e to the x, I'm going to do derivative of the first, so the first function, which is x to the 5th, times the second function, plus the derivative of the second function times the first. I'm writing them in the different order than what I just said, but we will write x to the 5th in front of e to the x. Okay, so that's the first derivative. It generated 2 terms, but now each term has a product of 2 different things. So when we take the second derivative, we now have to use the product rule twice. So the second derivative of f with respect to x, all right, so 5x to the 4th times e to the x, derivative of the first, 20x cubed times the second e to the x, plus derivative of the second e to the x times the first, 5x to the 4th e to, okay, 5x to the 4th e to the x. That is all from that first term from the first derivative. The second term of the first derivative, we use the product rule again. Derivative of the first, 5x to the 4th times the second e to the x, plus derivative of the second times the first, x to the 5th e to the x. Lastly, if we can, we might be able to combine like terms here, and I think I see a place where we can do that. Both of our factors of the term have to be exactly the same. So we could rewrite this as 20x cubed e to the x plus 10x to the 4th e to the x. So when I say combine like terms, we can combine 5x to the 4th e to the x plus 5x to the 4th e to the x. And then lastly, we still have x to the 5th e to the x. So these are the only two we can combine because both the e to the x factor and the x to the fourth factor are the same. All right, who knows? There's other ways we could write that. We could factor out e to the x. We could do some other, we could factor out x cubed. Actually, as I say that, I think it's worth just looking at that real fast. If I factored out x cubed e to the x, I'd be left with 20 plus 10x plus x squared. It's just good to practice the different algebraic manipulations or equivalent expressions to become fluid at those.